Good morning and good evening. Welcome to the Moonshot International Symposium for Goal 1 and Goal 3. Thank you for joining us today. In today's session, Session 2, we will welcome the Program Director and Project Managers of Moonshot Goal 3. They will explain about the goal and the research projects that will help achieve this goal. Then we will have a panel discussion with our esteemed international guests. For our audience, if you have any questions or comments, please feel free to put them in Zoom's Q&A box. We will select some questions to answer during the panel discussion. Now, let me invite Professor Fukuda, Program Director of Moonshot Goal 3, to give us an overview of this goal. Professor Fukuda, over to you.
Thank you very much, Bob-san. Okay. Hello. Good morning or good evening. I'm Toshi Fukuda. I'm responsible for Moonshot Goal number 3, the realization of AI robot that autonomously learn, adapt to the environment, evolve itself, intelligence, and act alongside human being by 2050. So next slide, please. So the motivation of this Moonshot program, particularly for this goal number 3, is we consider Japan's declining birth rate and aging population, that we need a robot in all aspects of society, working in dangerous or unstaffed sites, developing human frontiers, and supporting our everyday lives. Robots must be able to learn, act on their own through collaboration of AI and robots. Our R&D aim to realize AI robots with advanced bodies and self-developed AI learning. Next, please. So this picture is a society 5.0 concept of Japanese government. That's great. So by 2050, we'll develop AI robots that have the same or greater sensibility and physical abilities than humans and grow together with humans. Next, please. So this is a kind of a concept of Moonshot Goal 3. So look at the left-hand side, robot go together with a human, so working in somewhere and go to such a kind of dangerous site, or sometimes there's some kind of moon over there, so construct such infrastructure over there, such a kind of remote places. And also sometimes they can also working for discovery or solving a difficult kind of questions to make us optimize the solution. So that's a kind of very scientific task engaged robot. So right-hand side, robot work together from the beginning with as a human born, such like that, saying robot working together from the birthplace to say something like that, from cradle to all the kind of, to the end of the life, something like that. So next slide, please. That's once again our vision is a partner AI robot, and with grow with owner from the cradle to grave, so to say, and enhance the quality of human lives. So partner AI robot will watch our children, perform health management, and nursing care, and provide a variety of support for human customized for the personality and age. Next slide, please. So our vision is a AI robot will gain with all kind of ability to repair themselves, correct their own effort through experience, and improve their capability. Second is AI robot will make their own scientific discoveries, as I said, by thinking and acting autonomously. They will also inspire humans to make a new discovery too. Also, AI robot will work autonomously in extreme environment, protecting human life in such a disaster, or some kind of construct infrastructure on the moon, something like that. Next slide, please. So I have 4 projects in my Moonshot Goal 3. So can say one is Professor Shigeki Sugano. He will talk after me. Okay. Next is Professor Nagatani. He will talk about infrastructure robot. Third is kind of Professor Harada. So she will talk about such a kind of scientific robot. Then next is a kind of Hirata going to talk about such a adapted robot. The project is such a kind of 4 project. They locate, next slide please. Next slide please. Yes, there's that's a kind of 4 project. Locate in this way is such a kind of R&D for growing in the harmony with the human life, the kind of vertical line, down the R&D for judging and growing autonomously. Left hand side, robot-oriented study. Right is AI-oriented study. So that's a 4 project locate in this way, like in such a kind of very nice combined way to make this kind of collaboration and self-organization of our future robot. Next, please. For the future, that's a kind of we are going to make such a propel the cutting-edge R&D efficiently by promoting cooperation with overseas organizations such as NSF, Science National Foundation, or like a Department of Energy, like yesterday, Horizon Europe, Australia, and many other countries in the globe, also like IROS conference, and more. We would like to cooperate with the companies, industry, aiming for social implementation according to progress. Also, we discuss social accessibility of AI robot, including safety, security, and LC Pacific, particularly kind of such a ethics with AI, such a kind of National Science Foundation is aiming at. So also we'd like to hold regular event, drawing out from a synergetic effect through cooperation between program managers, program leaders, that within Goal 3 meeting and workshop in collaboration with other Moonshot goals, special goal number 1, such as avatar, cybernetic avatar program. Thank you very much for your joining today for our today's morning session. And I just outlined the Moonshot program goal number 3, such a kind of intelligent robot, such a AI robot. That makes such a kind of our goal 2050. Our life will be wonderful. I hope that try to make such a kind of great effort together with all of you. Thank you very much.
Thank you, Professor Fukuda. Now, let's move on to the project's overview presented by the project managers. The first project manager is Professor Sugano Shigeki from Waseda University. Professor Sugano, over to you.
So good morning or good evening, everyone. My name is Shigeki Sugano from Waseda University. So my project titles Smart Robot that is close to one person for a lifetime. We call that robot ILEC. ILEC is an abbreviation for AI-driven robot for embrace and care. So I have developed so many human symbiotic robots so far. So now in the Moonshot project, I will make a great jump from these kind of robots. So this is a goal image of a project. So one robot can do everything. So one robot can do everything. One robot is very important. There's not so many kinds of robots. One robot can in the work in business and housework and healthcare, nursing care, and finally it's medical treatment. So this kind of robot will be soft and general purpose robot. So as you know, there are so many kinds of goods. Cellular phone, camera, game machine, and PC, etc. But now we have smartphone. So in the case of robot, it's the same situation. Now we have many kinds of robots, but near future in 2050, so we have some smart robot. So we now set the autonomous level for smart robot. So as you know, in the automobile, there is a autonomous driving. There is level 0 to level 5. So in the autonomous robot, almost same as situation. So first go to level, now the level 1 and level 2, routine autonomous, corporate autonomous, semi-autonomous, and fully autonomous. So in 2030, we aim to realize level 3. So in 2030, so we will develop a smart robot level 3 with emotional interaction capabilities that can perform customer service, household tasks, such as cooking and wiping, nursing care, such as walking assistance and bed bath, and some medical tasks such as nursing and anthropography. The robot will be tested and operated in public facilities, homes, nursing homes, and medical facilities. So you can see this illustration. So the important point to develop ILEC, so AI and robots co-evolve based on various social needs. So there are 3 parts. One is robot innovation. So I will try to develop driver robots with flexible bodies for physical interactions that realize intelligent behaviors. And there's a big important point, AI innovation. Maximize the capability of software robots through human skill transfer. It's imitation by predictive learning. So this soft robot and AI, that combination is very, very important. But also we have to investigate about the social needs. So selecting necessary and appropriate functions through research on the social needs of AI generation, especially for Generation Z. So this ILEC's top challenge is to transform AI from software to software plus hardware. Of course, there is a background to have to develop OS, we call it LOS 50. So now I'll explain about that to software plus hardware embodied intelligence. Embodied intelligence, there are some papers about that, but our project aims to realize truly embodied intelligence. That means that compliance of the hardware and deep predictive learning, this combination is very important. In the case, in the part of compliance soft hardware, derived hybrid mechanism, elastomer and fluid materials, self-preservation biological system, and self-recovery system. And in the AI part, deep predictive learning, based on this learning system, we try to realize real-time prediction, control of sensory motor value, transfer human skills to robot, and the acquisition of the subjective world model. And probably finally, it's realized embodied emotional reaction. You can see this robot, it's an example of embodied intelligence. There already you show that this robot can hold a towel, but it's that robot also have the capability to hold the books and the other colors. So it means also this robot has some soft joint in the wrist. So then the vision and the environment and the force sensors, also the hardware, all are included in the AI learning system. That means embodied intelligence. So hardware is very important. Design of hardware and learning system combination is realized embodied intelligence. So about the hardware innovation of the year 2050, it's an example we are now designing. So elastomeric actuator, and spherical joint with materials. Probably it's including some elastomer, and it's some self-recover system. It's also included. It's we call dry wet robot mechanism. So conventional type robot is all dry robot. Now we realize dry wet hybrid robot mechanism. Also about the AI, I already mentioned about that. Finally, it's a kind of emotion system. It's you can see this autonomous nervous system on it's a biological reaction. That function is very important to realize new AI. It's cognition and precision. This is a loop about in the AI. There is an input of sensory stimulus, and it makes a prediction error. But that main point is that this hardware system. So finally, probably it makes here the self-preservation biological system and deep predictive learning is combined. Then we can bring the new AI embodiment intelligence. Okay, also I explained about the technology for welfare and medical care with smart robots, ILEC. So in 2050s, I tried to realize in the case nursing care, and medical care. It's example transfer support, pacing support, meal assistance, diagnostic tests, injection, and surgery. So there are many kinds of very difficult subjects, but in the ILEC project, I try to realize this case. And this is some illustration and some combination of the many kinds of hands, and also I tried finally the one robot can do everything. The another important point is evaluation of social needs and acceptability. So now it is very difficult to have the field experiments in the all over the world. So then now it is a limitation that specific robots or experiments in specific regions only. So we should have the discussion international standards, but there is now it rare. So this is a problem now. Then we try to realize this process to 23, understand needs for standard design. It's a quantitative survey. So comparison survey from 10,000 young people. It's Generation Z in Europe, US, Asia, and we try to 3 to 8 countries. So it's a very important investigation to identify what is important to design the new AI robot. So 2025, so feedback, and we'll hold the international symposium on LC, and 2030, establish a path for social implementation, including international cultural differences. Then we bring to this knowledge and experience to reflect the design of the AI robot ILEC. And this is my project organizations. There is 4-part R&D goal 1, body and control system for smart robots, and goal 2, AI systems for smart robots, goal 3, technology for welfare and medical care with smart robots, and goal 4 is practical measures for smart robots. So now we are 1, 2, 3, 4, 5, 6, 7, 9 professors, including this project. And also we have a technical collaboration, AIST and the Alan Turing Institute, and social research collaboration with Harvard University and University of Cambridge. So there is a R&D issue here. So please see this slide. So there are innovation, robot innovations, social needs analysis, and social implementations. So that is a plan to 2050 in the hardware innovation, social implementation, and social survey. So that's all. Thank you very much.
Thank you, Professor Sugano. The next project manager is Professor Nagatani Keiji from the University of Tokyo. Professor Nagatani, over to you.
Good morning, good evening, everybody. This is Keiji Nagatani from the University of Tokyo. Today, I will introduce a project entitled Collaborative AI Robots for Adaptation of Diverse Environment and Innovation of Infrastructure Construction. In this project, we have set two technologies expected by society in 2050. The first is natural disasters response caused by global warming, and the second is establishment of base for manned exploration on the moon. In Japan, further technologies of natural disaster response is desired because of frequent natural disasters. On the other hand, it is necessary to promote international cooperation in lunar development, such as the Artemis project led by the United States. Both of these technologies have one thing in common. They require field robot systems that can adapt to various environments to build infrastructure. Our goal is to realize such field robot systems. This illustration shows an image of emergency response using multiple field robots at a natural disaster site in 2050. Robots obtain sensing data to understand the environment, conduct collaborative works to respond to unexpected situations, and perform disaster response. This illustration shows an image of infrastructure construction on the moon in 2050. In this illustration, multiple field robots autonomously perform collaborative work to build infrastructures while responding to unexpected situations. Here, I would like to explain a little bit about the difficulty of realizing field robot systems. In current mainstream approaches to robot design, firstly, the situation, or I can say environment, is assumed. And then the hardware and the software are designed according to the situation. After the robot is deployed in the target environment, it executes the task by optimal motion planning. During the execution, the robot obtains sensing data and adjusts its motion to perform the task robustly. We call this approach closed design. This approach is effective for robots in factories, and the application of the robot is expanding in the world. On the other hand, this approach does not work well for field robot systems in case that the target environment is a disaster site or even a construction site. According to this approach, it is necessary to design the hardware and the software for all possible situations. After the robot is deployed in the target environment, it executes the task by planning result according to the situation. The key is to understand the situation by robots in an ever-changing environment. During the task execution, robot's motion should be conducted based on sensing data. However, in the field, much higher sensing ability is required than in a factory. Therefore, a robot with a closed design is expected to fail. That is because it is difficult to predict the boundary conditions of the target environment at the robot design phase. Therefore, the design problem is not closed. In the design issues for disaster response, the time, place, and scale of the disaster cannot be determined. It is difficult to grasp the situation because of an ever-changing environment. The solution is not simple, and there is no right answer. In the design issues for infra development on the moon, the environment is uncertain, particularly there is a lack of knowledge about the ground. There is a high possibility of equipment failure and impossible to repair it. Information is limited available in remote areas and communication delays. Therefore, in addition to the conventional closed design, we will introduce a concept of open design for robot in our project, which has been lacking in the past design. We categorize the open design in 3 research areas: body, measurement, and control. For the research of the body, we will consider flexible robots that fit in with the environment. For the research of measurement, we will consider environment evaluation AI with many modalities. For the research of control, we consider dynamic collaborative physical AI using multiple robots. We aim to realize field robot systems that can respond flexibly by conducting these researches. In order to realize such a robotic system, this project has set specific goals for the next 5 years. As for the goal of emergency response for natural disasters, we focus on a disaster of river channel blockages, or so-called natural dams. The blockage is occurred by a landslide caused by an earthquake or heavy rainfall, which blocks the river. The gradually accumulating water will eventually overflow and cause a mudslide, resulting in major damage downstream. In this project, a series of disaster response scenarios, such as information gathering, risk assessment, sediment transport, and drainage pump installation will be set up, and an actual multi-robot system will conduct these scenarios. On the other hand, our goal is to realize a robotic system to build the moon-based infrastructure. Specifically, the goal is to build a robotic system to construct a land base for a transport aircraft. Currently, many countries, including Japan, are studying the scenario of lunar-based construction. However, there is little scenario on constructing of the base. In this project, we will develop technologies for ground surveillance, preparation ground, and ground compaction using collaborative small robots to construct a landing base. In addition, we aim to realize the construction demonstration using multi-robots in JAXA's indoor simulated environment. In the last slide, I will introduce a process diagram of this project. The horizontal axis represents environmental unknowns, and the vertical axis represents the autonomy necessity. Natural disaster response is located on the right side because the environmental unknown is greater. On the other hand, construction of lunar infrastructure is located on the upper side because the autonomy necessity is high. The common infrastructure technology to realize both, named adaptive construction, is located between them. To achieve the adaptive construction, we will promote researches related to flexible robots, evaluation AI, and dynamic collaboration. The technology of adaptive construction can also be applied to social infrastructures and contribute to the stable supply of them. Also, the system integrations for both lunar and natural disaster response will be carried out in parallel and contribute to them directly. Finally, I hope that our research activity will contribute field robot systems that can adapt to various environments based on open design. That's all. Thank you for your attention.
Thank you, Professor Nagatani. The next project manager is Professor Harada Kanoko, also from the University of Tokyo. Professor Harada, over to you.
Okay, so good morning and good evening, everyone. I'm Kanako Harada, the University of Tokyo, and I'm a project manager of the co-evolution of human and AI robot to expand science frontiers project. Okay, sorry. Okay, so first, let me share our vision, taking an example of a day of a scientist in 2050. The scientist would think that I want to try the chemical on the cell, but it's difficult for me to manipulate the small, soft, and deformable cells. So the scientist asked the robot, can you mix chemical A and B and inject to the cell by varying the quantity and the location? The robot would say that, oh, let me give it a try. And I'm bad at mixing, so I will work with the mixing robot. It's a self-organization of functions, sometimes by inviting a peer robot. And then the robot would say that this is the best condition and the simultaneous injection at this location worked well. And sometimes this is what the human scientist cannot perform due to the limitation of dexterity. Then the scientist would say that, oh, it's interesting and it would work for another type of cell. And by this inspiration, scientists can plan another experiment. And we think that this is a part of co-evolution of human and AI robots that we are dreaming of and would propel the concept that everybody can be a scientist. So, so we are proposing the collaboration of AI robots scientists and human scientists. And AI robot scientist can perform hypothesis and analysis by its AI, and also the observation and the manipulation by its robotic technology. And these can be something that scientists don't even think of or cannot imagine of. Then the human scientist can interact with AI robot scientists to get inspiration. So this is our vision. And by discussing with our colleagues about this concept, we came to think about an idea that evolution of science can be somehow similar to the evolution of AI robot. So this inner circle is how the scientists would evolve. So the scientists start from the hypothesis that will lead to a desired outcome. Then they design experiment to verify the hypothesis. Then they do action on unknown system, then observe to learn the hidden structure in the system for better understanding of the system that would eventually lead to the discovery of theory. And the evolution of AI robots would have the same circulation. So we start from the hypothesis leading to a desired outcome, like manipulation, then design experiment to verify the hypothesis, then do the manipulation on unknown system. Having the robot in this system is, that in addition to observing the phenomena, we can add different manipulation and observe a different reaction to them. And then we analyze the outcome to learn the hidden structure in a system to better understanding of the system, leading to the discovery of the strategy. So, by observing this, we can say that developing AI robots for science is to evolve AI robot technology. And we can also say that the AI robot fully advanced will be capable of science investigation. So we keep this in our mind during this project. And in this project, we decided to focus on the science experiments on plants and animals. So we, for the pesticide-free and drought-resistant plants, we study medicines for plants. They're called biostimulants. And we also study nutrition for plants to study plant regeneration in an optimal culture medium. And for the animal study, we propose in total biology is to observe organoids They are the small mini human organs under blood circulation condition to study mechanism of organ development or the development of new medicine in a challenging environment like a biohazardous environment, super clean or a low oxygen environment. So in the next 10 years, we are going to develop science AI robot team for science experiments on plants and animals in a challenging environment. So let me summarize the challenges for this science AI robot team. First, it should work in a challenging environment where people cannot stay or do not want to stay long, like a biohazardous clean environment. And we expect large individual differences in samples and manipulation adaptive to the changes in the samples or environment is required. And then it's often true that the number of available samples is limited, and we need to discuss ethical issues, in particular for the experiments on animal. And then it's often true that the limited time duration is allowed for experiment on plants and animal. And the robot need to manipulate small, soft, and deformable samples in a wet condition. And the scientists often use qualitative metrics for evaluation, like it's good or bad or it's terrible. And looking at these items, we notice that these items are not only for the science AI robot, that these are common in many robotic applications, including the surgical robots I have been studying for years. So let me discuss a little bit more in detail. So I take the example of graping a small organ. So we start telemanipulation, and then we observe that the difference between novice just grip and crush, and the expert grip the tissues gently. But what is a grip gently? So we understand that gripping gently is to insert the tool tips underneath the organ, then pull up and grip with a small gap. And the position insert is decided by its anatomical knowledge. Then we do a design of the robotic cognition and manipulation, eventually to automate the robotic system for faster processing of multimodal big data, and also having a high dexterous accurate manipulation, which would lead to the improved success ratio and the faster processing, and also resulting in the efficient recovery. And another example is about the search for chemicals presenting desired reaction. When we plan the science experiments, we also observe that the difference between novice and expert can design experiment result in a large variation in result. So we study, how to lead to the desired outcome, and then search for the condition based on the strategy. Then we automate the system. It's the same as I said, it would result in the efficient discovery. Okay, so to make our dream come true, in the last slide, I present the team of our project, and this is the organization. And we decided to study a theory, implementation, and application at the same time in the same project. So the first team, we have researchers in physics and mathematics. And then we have AI researchers and robotic researchers to develop next generation AI robots. And we also involve users, they are scientists, also to study the application of the next generation AI robots. And I think that this team building is one of the most important key to the success, and I'm very proud of this team. So that's all for me. That's all for me, and I'm very looking forward to updating you with our result very soon. Thank you.
Thank you, Professor Harada. Moving on, the next project manager is Professor Hirata Yasuhisa from Tohoku University. Professor Hirata, over to you.
Okay, thanks for introduction. Good morning and good evening, everyone. So I'm Yasuhisa Hirata from Tohoku University. So today, I'd like to explain our Moonshot project entitled Adaptable AI-enabled robot to create vibrant society. Okay, first of all, let me explain my vision of the society of 2050. I believe that in 2050, robots will be everywhere in our daily lives, and we will all be using them naturally. Even now, many people are using shared bicycle to get around the city easily. Also, when you go to ski resort, you can enjoy skiing by renting ski equipment. So in the future, robots will be shared and used everywhere in our daily life. On the other hand, we don't want to develop robots that exist as tools, like shared bicycles or skiing equipment. Our goal is to develop AI robots that can provide appropriate support and services depending on where they are used and the condition of the users. So we'd like to call such robots adaptable AI robots. So adaptable AI robots will be used not only in homes, but also in commercial facilities, cultural facilities, sightseeing spots, sports facilities, nursing homes, hospitals, child care facilities, and many other places as part of the infrastructure of society. So we aim to envision a smarter, inclusive society where everyone lives a healthy life by coexisting with AI robots, and its society cultivating the feeling of I want to do or to be something, and fulfills it using AI robots. So in order to realize a new life with AI robots, we have set up 3 major research topics. The first is AI-related research to design how robots should behave in order to provide appropriate assistance and services to humans. The second is research on robot hardware to provide safe and appropriate assistance to humans. The third is research on social implementation, where AI and robot hardware mutually evolve and AI robots can be used in everyday life. So today, I'd like to briefly introduce these 3 research topics. So first, I'd like to explain our research on AI to design the behavior of robots. So our goal is to develop AI robots that encourage people to act on their own without providing excessive assistance. So for this purpose, we focus on the concept of self-efficacy in this project. So self-efficacy is the expectation of how well you can perform actions necessary to produce a certain result, and the recognition of the possibility of your own action. If the self-efficacy is low, a person hesitates to try new things, thinking that I cannot do it, or that I might cause trouble for others. On the other hand, if the self-efficacy is high, a person tries new things, thinking that I can do them by myself. The aim of this project is to find out a mechanism of change in self-efficacy, feeling like I may be to do it, or I will try it. Along with this approach, we aim to set appropriate goals for each task for improving self-efficacy and to design behaviors of AI robots. So there have been several studies on improving self-efficacy, but most of them focus on short-term human observation and assist, dealing with limited tasks. So on the other hand, we want to develop an AI robot that can improve self-efficacy through long-term observation of the user and encourage him or her to take on new challenges. So in this project, we will focus on learning from skilled people for improving self-efficacy. For example, the advice and support of skilled coaches in sports and skilled therapists in nursing care and rehabilitation are very, very effective. Therefore, if the AI robots realize the ability of skilled people, everyone will be able to receive coaching and support to improve their self-efficacy. So furthermore, if multiple AI robots installed in various places can continuously watch over a person, it will be possible to find the most appropriate support and services for that person, which even skilled people are not aware of. The second research topic is the hardware of adaptable AI robots. So our robots are designed to provide services to people of all ages and physical condition, and to be adaptable for many purposes. In order to achieve this goal, a single robot with a fixed shape may not be able to provide sufficient support. Therefore, we aim to develop adaptable AI robots that can change their shape and form according to the user's condition, environment, and the purpose of the task, and provide appropriate assistance to encourage the user to take independent action. So in this project, we propose a new concept called robotic nimbus. You may be familiar with the flying nimbus, which is a cloud-type flying vehicle that appears in the Dragon Ball manga. The word nimbus means a splendid atmosphere or aura that surrounding a person or thing. The concept of our proposed robotic nimbus is to assist the user's perspective, proactive actions naturally while transforming into various shapes like a cloud and gently enveloping the user. Although we would like to develop various robots based on the concept of robotic nimbus in the future, so first of all, we will develop nimbus holder, nimbus wear, and nimbus limb. The nimbus holder gently and firmly supports humans, aiming to support stable movement by restraining the movement of upper and lower limbs, and to support walking and standing of people with lower limb disabilities. In addition, we will develop nimbus wear, a light and comfortable assist wear. By wearing the nimbus wear, we aim not only to realize power assist and motion guidance, but also to relieve human tension and anxiety by controlling the wearer's comfort based on human sensing. In addition, we will develop nimbus limbs, which aim to extend human motor and work capabilities using the third and fourth arms and legs. So currently in Japan, the concept of a future society called Society 5.0 is being proposed. Society 5.0 represents a society in which cyberspace and the physical space are highly integrated. So while cloud computing in cyberspace is progressing, we aim to realize a cloud that enables safe and secure interaction in physical space, that is robotic nimbus, as a social infrastructure. So finally, the third research topic focuses on how to implement the proposed adaptable AI robots that improve self-efficacy in society. So in order for AI robots to be accepted by humans and society, it is important to obtain a social consensus on how to control the robot from the perspective of ethics and law, as well as personal information protection. So it is also necessary to establish safety evaluation standards for adaptable AI robots so that all people can use them. In addition, the fact that AI robots are installed everywhere as a part of social infrastructure means that the people don't always use the same AI robot. We aim to develop a technology to share the experience of user AI robot interaction with other AI robots, so that even if the AI robot has a different form or function, the user can recognize it as a usual AI robot that knows him or her well. So our ultimate goal in 2050 is to create a society in which everyone can play an active role by improving their self-efficacy through coexistence with adaptable AI robots. In order to achieve this goal, we define the level of self-efficacy for each individual and aim to rise that level one by one. We will start by supporting single movements such as standing, walking, or reaching, and then aim to support a specific task consisted of several movements. So once the user is able to perform the specific task, we aim to support the challenge of similar tasks and new tasks so that user will eventually want to proactively participate in society, thus realizing a vibrant society, which is the title of our project. So finally, I'd like to explain our milestone for the year 2030. The milestone is to show that adaptable AI robots proposed today can be driving force for creating a vibrant society in which everyone can participate enthusiastically, not only in daily life, but also in travel, sports, and other activities. So if this milestone can be achieved, the adaptable AI robots will be able to use in various fields. But in this project, firstly, we aim to achieve this milestone through demonstrations in the field of nursing care. This is because Japan's current support super aging society has a variety of problems. So for example, in 2019, there were about 300,000 people who could not enter a special nursing home even if they wanted to. So it is also reported that there will be a shortage of about 800,000 nursing care workers in 2035. In addition, in 2070, about 90,000 people left the workforce because of family care. To address the challenge of the super aging society, we will propose both innovative solutions that can be used in the future as a moonshot and a realistic solution that can be adapted to the near future. So finally, this project will be carried out with many researchers and institutions shown here. Thank you very much for your kind attention.
Thank you, Professor Hirata. Now it's time to move on to our panel discussion. The moderator for our panel discussion will be Professor Ueda, a sub-program director of Moonshot Goal 3. Professor Ueda, over to you.
Okay, good morning and good evening. I'm now Nuri Ueda. I'll be the moderator of this panel discussion. So before the panel discussion, I'd like to have a presentation from the three guests from abroad. So first presentation is Professor Ken Goldberg from UC Berkeley. Let me introduce him briefly. So he's the William S. Freud Distinguished Chair in Engineering at UC Berkeley and an award-winning robotics filmmaker, artist, and a popular public speaker on AI and robotics. He has published over 300 papers, 3 books, and holds 9 US patents. With unique skills in communication and creative problem-solving, invention, and thinking on the edge, he has presented over 600 invited lectures at events around the world. Okay, Professor Goldberg, over to you.
Thank you. It's a pleasure to be here. And can you hear me okay? Can you see the slides?
Yes, please.
Okay, very good. So what I'd like to do in this, in honor of this wonderful kickoff of this new program is to talk about what I believe is a hopeful vision for humans, artificial intelligence, and robots in the year 2050. So this evolution has been going on for many years. In fact, this year we're celebrating the 100th anniversary of the word robot that was coined in a Czech play, 1920. And as other colleagues have mentioned, there's been enormous progress. In fact, in the last decade, work on deep learning has made a major advance in artificial intelligence, and it's due to massive data sets, computing, and new algorithms under the title of deep learning. Everyone's aware of the major result when the system AlphaGo beat the world champion at the game of Go, and it was hailed as a major breakthrough. It's also important to remember that this was a very complex game and with a very large branching factor, but it's also a game, meaning that there is a lot of complexity, but the state of the board is fully observed. It's known perfectly. It's a 19 by 19 grid. It's a trinary state environment. So there's either each cell is either empty or has a black or white stone. So we know exactly what the state of the system is, and it's stationary. It waits for the opponent to make a move. And I want to contrast that with the complexities we're talking about today, which is in the real world, where we have vast amount of complexity, where the environment is much bigger than a 19 by 19 grid. The complexity of each cell is far more than just trinary, and the system is dynamic and highly uncertain. So really important to keep in mind that games are not reality, and reality is still a very, very difficult objective. So what I want to list very quickly is some moonshots that I see for the year 2050. And I'll start with grasping. And we might start with this scenario where many of you are familiar. We're ordering more and more objects than ever before. In fact, e-commerce sales have been steadily rising, but this year something dramatic happened where the e-commerce had been accelerated by COVID-19. Many more people are staying at home and ordering things than ever before. And this is causing a major challenge for the e-commerce systems because it's not possible to fulfill these orders, this great increase in demand because of COVID-19 again, because there's not enough workers who can work in close proximity. So this has driven a renewed interest in the grand challenge of robot grasping, being able to pick up an arbitrary object and manipulate it. And this is still a grand challenge for our field. And if we could solve it, this would have enormous impact in warehouses, in factories, and homes. So in homes, let's consider something like this. You might go to work in the morning and you leave your kitchen, and wouldn't it be nice if you could come home a few hours later and it would look like this? So if we had robots, as we're talking about today, that would be able to clean your home, it would be enormously valuable. And this requires the ability to pick things up. Now, there have been major advances in computer vision. We can now see things, robots can now see things that they couldn't before. So this has been very, very exciting. And the ability to label objects, and it was largely due to the ability of the existence of data sets, very large data sets in computer vision, labeled data sets. So we've been looking into the analogy of could we come up with very large data sets of labeled objects for grasping? And this is the idea behind the dexterity net, or DexNet, not ImageNet, but DexNet, that my students and I have been working on. And the idea here is to mathematically study each of the objects in that data set, and then look for optimal grasps that are robust to small perturbations, the inevitable uncertainty in position, orientation, and uncertainties in the mass of the objects and the friction properties. And we can use Monte Carlo integration to then take all those samples and in simulation and come up with predictions of how reliable different grasps are, how robust they will be in practice. So the one on the left is not very robust, the one on the right is much more robust. And so this is the result of our system. It's been running on a number of different scenarios. These are objects it was not trained on, but using deep learning, it has been able to generalize and to be able to pick up new objects with very surprising degrees of reliability. This is DexNet in action. It's not working all the time, but what you can see is the numbers in the upper right are conveying what is its progress, how is it doing over time. And it's also making use of depth sensing, which is another major advance. Now, I also want to mention the technology of 5G. 5G networks are growing all over the world. They're increasing speeds and robustness, throughput and latency of networks. And this is combining with the Internet of Things. This is growing for many devices, not only robots, but sensors and small actuators that are being placed all around our environments. And these come together with robots in what is sometimes known as cloud robotics, a term coined by James Kuffner at Toyota. And here the idea is that we can make use of data in the cloud and also cloud computing so that all the computing doesn't have to be done on board the robot. And I wanted to say we are even interested in taking this a step further now because we're recognizing that the computing is not either done all in the cloud or all on the edge, but actually in all kinds of layers in the larger infrastructure. So it's not all in the cloud or the ground, but we call it fog robotics. That's the hybrid of robots in both places. And this is very exciting, this idea of combining Internet of Things, 5G, and fog robotics together in the coming decades. This is going to have impact, by the way, I believe, in many different industries around the world. In fact, there was a lot of talk about the fourth industrial revolution, which is now going to be realized in the context of intelligence, but I also want to keep in mind that I believe that it's going to also involve humans at all levels. Now, let's talk about deformable objects, and I want to note in the context of our aging population that Fukuda-san had mentioned at the onset that we have an aging population in all countries today. In fact, in Japan, it's very acute. There's this idea that very soon we'll only have 2 working people for every retired person, which puts a lot of pressure on the system, on the society. But if we had robots like this that would be able to go in and keep our homes tidy, would be very, very appealing, because it would be good for our well-being, our peace of mind, also for safety, because you can trip over these objects and fall and hurt yourself on such things, especially for older citizens, senior citizens. So this is not impossible, though this system is still a prototype. The challenge is, how do we pick up and manipulate, in particular, soft objects like that are something like bed sheets. And so we've been doing a project with Toyota, Honda, on working on making beds, which is something no one likes to do, but using depth sensors and deep learning to be able to find pick points where to put the robot gripper in order to effectively make the bed. And so we've been learning these through examples, and then here's a quick example of the system in one set making a bed. It's a small scale bed, but we're making progress on this, and I think that we'll be able to see that in the next decade. Also, we've been looking at untangling things like ropes, untying knots, and then organizing things from clutter to reorganizing them nice and neatly. So here's an example of a robot untangling a fairly straightforward knot. And we've been able to do this with very high reliability. We're also just starting a new program with the Toyota Research Institute, which will be a 3-year program to look at 1-dimensional deformable objects like strings, 2-dimensional objects like sheets, and 3-dimensional objects like solids, and being able to manipulate those with robots, which are still frontiers of challenges right now. So I want to just end by saying that artificial intelligence is very exciting and has great potential, but I also think it's very important for, as we've been talking about today, that it will also be related to intelligence amplification of our human skills, the self-efficacy that Harada-san mentioned earlier. And this is because humans and robots are complementary. Machines are very good at precision and calculation, but humans are still very good at understanding and empathy and dexterity. So I think this complementarity makes a lot of sense and is very natural in Japan, where the idea of Astro Boy and robots as friends and companions has a very long and rich history. We've been working on thinking about how this also it relates to diversity, enhancing diversity in populations, that robots can allow us to do what it is that we are uniquely meant to do, to focus on high-level thinking, strategy, and paving the way for innovation in the future. So these are some moonshots that I have in mind. I'm looking forward to discussing with the other panelists. And I'll just mention in the end that I also believe there's going to be some great advances in robots for surgery and agriculture. Thank you.
Thank you very much, Professor Goldberg. Okay, so the next is Professor Katja Mombauer from the University of Waterloo. Let me introduce her briefly. So she joined the University of Waterloo in March 2020 as full professor and the Canada Excellence Research Chair for Human-Centered Robotics and Machine Intelligence. Prior to coming to Canada, she has been a full professor at the Institute of Computer Engineering of Heidelberg University and head of the Optimization, Robotics, and Biomechanics Chair, as well as the coordinator of the Heidelberg Center for Motion Research. Her research focuses on understanding human movement by a combined approach of model-based optimization and experiment, and using this knowledge to improve motion of humanoid robots and the interaction of the humans with exoskeletons, processes, and external assistive devices. Okay, Professor Mombauer, over to you.
Okay, thank you very much for the kind introduction. So good morning and good evening, everyone. It's really my pleasure and an honor to be here at this very interesting Moonshot Symposium. So I will tell you about our research on endowing human-centered robotics with motion intelligence and our vision for robotics in 2050. So what are these human-centered robots I'm talking about? So I would define them as all the robots that closely work with humans, that somehow support humans in their actions and motions, and so that work on humans, or that perform human-like tasks. And these human-centered robots, they may come in very different shapes, and they may have very different functions and tasks. So one of the visions is that human-centered robots can support and facilitate people's lives in many areas. For example, they should be able to replace humans in dangerous, remote, and also in monotonous tasks. So we already saw a few examples of that in the previous talks. So for example, robots helping in disaster recovery, performing work in space, to name a few very remote and autonomous tasks, but they are also supposed to help in airplane and chip manufacturing. But there's also a completely new set of dangerous tasks that just came up in the past year related to the COVID pandemic, and there the danger came from being close to humans. So robots could also have taken over some of the jobs that in care and nursing, but also in medical testing and anamnesis to keep medical personnel safe. And here these tasks, they range really from very remote standalone tasks to very close interactions with humans, which robots could take. On the other hand, human-centered robots can support people's lives by enhancing human mobility and well-being, by supporting humans in many ways to help them lead an independent life. We also heard examples for that already. So this ranges, and this relates to robots of very different shapes from the ones we saw before. So these are exoskeletons, prosthetic technology, assistive mobility devices, which really have to satisfy very individual requirements for each of the persons. But that also includes all kinds of household helpers or other kind of companion robots helping people to be independent at home. So the robots have to, in order to do that, the robots have to intelligently interact with humans, learn to collaborate with humans, assist and support human movement, and also predict the consequences of their actions. They have to explore unknown environments, and they also have to interact with the environment. So why is, sorry, I jumped one. So what kind of intelligence do human-centered robots need for these tasks? Of course, for each of those tasks, also a specific artificial intelligence in the classical sense is required. So for any of the medical tasks or manufacturing tasks, of course, the specific skills are required to perform the actions and sequences. But one thing that is common in all these cases is that the robots require motion intelligence. So they need the ability to perceive the environment and interact with the human partners. They need cognitive skills to understand what they perceive and also take the decisions about what to do next. They need the ability to predict or anticipate what will happen next, what the human will be doing next. They need a strong motion ability. So they have to be strong enough, fast enough, efficient enough, stable enough to perform the motion. And that's still one of the big challenges right now in robotics. And of course, they also need the ability to interact. So to interact with the humans and the environment in a safe, reliable and predictable way. So also they have to be predictable from the human perspective. So this motion intelligence is also what is sometimes referred to as embodied intelligence, which is really completely different from just the classical artificial intelligence. So why is this motion intelligence so difficult, especially for the humans? We are talking either about robots that have a human-like shape or robots that are acting on a human figure. So the problem is it's a highly complex system with many degrees of freedom. They are redundant with respect to the movement task. So there's many different ways of doing one particular movement. System is under-actuated. We have a complex stability control, so the robots easily fall and the humans easily fall, and also motions easily get infeasible. So in order to solve all these tasks, the pure machine learning approaches can unfortunately not help. So one of the things we need for human-centered robots is really a fundamental understanding of how human movement works in all the different situations we are looking at. So this is a big part of our research, to look at everyday motions, all the motions we are trying to support, or all the motions the robots are supposed to perform. Another thing which is required are efficient models and algorithms for motion optimization, learning, and control. So learning these very challenging motions from scratch is not possible for humanoid robots, and also not for exoskeletons that work with the human in the loop. So because robots and humans would be highly damaged. So we think that models, physical models or models of the underlying physics of the robot or the humans can be exploited to find feasible motions and motion ranges. So definitely model-based approaches should play a role, but we think the real future will be to look for combinations of model-free and model-based methods to tackle these systems. So show you a few examples from our research. So one of the big problems today is back pain, which that's one of the reasons for people not being well. So back pain is one of the leading causes for sick leaves. Here robotic technology can help a lot. We have helped to develop spinal exoskeletons for preventing back pain, and also for reintegration of workers. I've done a lot of research developing them to help workers that work in dangerous situations or have to lift heavy loads. Like optimization and model-based simulations play an important role in that, and they help us to develop the best possible exoskeletons, but also at the same time look at the ergonomic aspects and make sure even strong exoskeletons don't exert too high forces while interacting with the human. So we've used these techniques to determine best support by exoskeletons, but also to compare effects of training and motion adjustment to the effects of exoskeleton. The aging society has already been mentioned by previous speakers, and the loss of mobility is also a key problem here. We all know that the current support devices are very outdated, so we just have very rigid mechanical rollators, and here the development of new digital technologies and also intelligent mobility assistant robots is very important. But also of a comprehensive concept for preserving and improving the mobility of older people at very different levels of frailty. So we are looking into developing robotic walkers in that context, which is the follow-up of a European project, Mobot, that we have been part in. Here the idea is to develop different kinds of robotic devices for targeting people of different frailty levels, and allow them to still continue to walk and to stand up from sitting, even if they are not strong enough anymore, by having a robot that can predict what they are up to, but also give them a more active support than the classical walkers. We're also interested in exoskeleton and for older persons, but also for spinal cord injury patients. Here we work with an exoskeleton from IIT, and the goal is to achieve stable walking without crutches. We are planning to adjust some of the hardware and develop new controllers for elderly people, but also for spinal cord injury patients, and we are also developing procedures to make users feel more comfortable and safe when using the exoskeleton, which sometimes is a bit scary in the first place. We also work with humanoid robots a lot. Our main platform is the Wing C robot, but we also are able to work with a Talos robot, which is available in the Waterloo RoboHub. Some of the things we are doing include motion improvement and benchmarking. So we want to teach robots to move on different terrains, but we also are developing benchmark to evaluate how robots will work in real life situations in collaboration with the Eurobench project. So,
sorry, your slide does not change.
Sorry?
Please check your computer.
You don't see my slides?
Yes.
Oh, that's okay. You didn't see any slides?
So current slide is the five motion intelligence with a challenge. The slide doesn't move.
Sorry?
So current slide is the title is five motion intelligence a challenge.
Okay,
so,
I have been. Okay, I have. Okay, I've.
Yeah.
Shown you lots of
It's okay.
slides. Okay, that's. Should I maybe stop sharing and then share again? I'm sorry for that. Add. Can you see it now?
Not yet. Yes.
Okay.
Okay.
Okay. So
Yeah.
Okay. So I've shown you all these slides.
Yeah, please go ahead. Yes.
Okay. So I will continue where I was. Okay, so we are also, then unfortunately you didn't see all the assistive devices I was showing you. But we also work with humanoid robots and are trying to teach them to move on different terrains, but also to develop benchmarks to evaluate how robots can move or can act in the real world. So we are developing controllers for stair climbing, but also for standing up from sitting, for walking over obstacles. We are also developing manipulation controllers for having robots manipulating objects, grabbing objects from shelves, carrying them around. We also work on controllers for tests for evaluating the stability of walking, which is one of the crucial aspects. Okay, one thing we think is really important is physical, social, human-robot interaction. So there is a lot of examples for which we need close physical human-robot interaction over extended periods, for example, in the medical field. But we think it's really important to check what it takes for humans to allow robots to enter in close contact with them. So on the one side, there's the field of physical human-robot interaction where people are trying to achieve a desired task in a way that is safe to the human. The current state of the art is that a lot of the interactions are still quite distant, and we're looking at joint manipulation, handing over of objects. On the other side, social human and robot interaction looks more at it looks how a task has to be performed to be psychologically and socially accepted by humans, and that makes humans feel comfortable. But the current state of the art in social robotics is more to look at speech and gestures and very distant interaction. So we think we have to really look at physical, social, human robot interaction that combines both aspects, because there's a lot of examples, for example, in social companion robots, but also in many medical applications where it is very crucial for robots to get very close to the human and interact with them or act on them for an extended amount of time. For example, COVID nasal swab testing is one of the medical problems we are looking at, and we are trying to find out what it takes physically, but also socially for a robot to get so close to a human and be allowed to do the tests. And of course, this is also a crucial aspect for mobility assistance robots, such as the robotic walkers, exoskeletons, and so on. Okay, so the outlook, human-centered robotics in 2050. I would say that by 2050, we will have all the discussed robotics technologies that can facilitate people's lives. The robots will be able to fully replace people in disaster sites, work in space, and take over the boring manufacturing jobs. They will be able of close physical, social, human-robot interaction, and they will also be highly adaptive to new situations. In the case of a pandemic in 2050, the robots would take the frontline jobs and help to keep medical personnel and patients safe. Of course, we hope that there will be none. We will have specialized robots to support persons with all kinds of mobility problems, allow them to move autonomously and prevent pain and injuries. And I also would say we will have companion and support robots that allow old persons to pursue an independent life, in addition to the mobility assistance robots mentioned before. So I think there will be many special robots with very different shapes, so humanoids, semi-humanoids, but also exoskeletons, but also many shapes we probably can't imagine yet, and also very different functionalities, and not one robot that can accomplish all tasks. With that, I'm at the end, and I thank you very much for your attention, and I apologize for the technical problems. Sorry for that.
Okay, thank you very much, Professor Mombauer. Okay, the next is Professor David Walter-Green from Carnegie Mellon University. Let me brief him. Let me introduce him briefly. So his research focuses on robotics exploration underwater, on the surface, and in air and space, and the necessary ingredient of perception, planning, learning, and control for robot autonomy. His current project is Moon Ranger, to search for water at the South Pole of the Moon by landing in 2022. Okay, Professor Walter-Green, over to you.
Thank you.
Yeah.
I'd like to speak today briefly about robotic explorers. So I'm thinking about robots as machines that can explore places where people can't go, places where people haven't been, being the explorers of the future. So here on Earth, but also as we see just in the news today, robots exploring the planets beyond Earth. So my research focus has been on enabling these robots to be more capable and explore in more difficult situations with more information gained on board the robot and utilized on board the robot. So where we are today is that these explorers are quite capable of navigation, getting from A to B, and collecting information along the way. It's still a challenge to be productive. So the photo you see on the right there is of the Curiosity rover, very similar to Perseverance that's just landed on Mars. It's going to spend a lot of its time waiting, waiting for information on what to do next, waiting for the data it's collected to be processed, and waiting for instructions on where to go and where to sample. This is because we rely so much on the human intelligence on the ground. We have very limited bandwidth, the amount that we can communicate, and often a very limited communication rate. So even robots that can communicate directly to Earth still have to wait for the antennas on Earth to be available to service them. There are many, many probes out there, many, many satellites, and it just takes time to talk to each of them. So these robots spend a lot of time on their own, waiting for instructions, waiting for information. So these are the challenges that are still quite difficult, being able to collect information and know that it's verifiable, know that it's calibrated, that it's of the correct target, that there are no errors that occurred in the collection of it, particularly when we're collecting physical samples or we're doing physical operations. Verifying that the operation went correctly still takes a person to look at those results and then communicate with the robot that it's ready to proceed. Knowing how to interpret the data. Right now, there's a little bit of work on these robots that allows them to interpret images and maybe find features in the image that are relevant for further investigation or detect dust storms or changes in the environment. But for the most part, all of the data interpretation is not performed by these autonomous systems. And this is a place where artificial intelligence will help us quite a bit. And lastly, as I've mentioned, deciding what to do next. Once information is collected, and maybe once it's interpreted, what to do with that information. So this is the area that I've focused my research on in recent years. And we're thinking to explorers today, but also for the next decade and beyond, and how do we imbue greater capability for exploration autonomously. So we take a map-driven approach because exploration often seeks to produce a map, whether it's a physical map of the environment, or it's a map of the physical properties, a map of the history, a map of the biology. We want to understand the relationship between these physical phenomena that we can observe and where they occur in the world. And from those relationships, then we're able to make further interpretation. But our process then, beginning with a map, we want to make best use of what's known in advance, whether that's coming from a human scientist or maybe some a priori sensing, for example, from remote sensors or satellites. Start with some initial map and use that map to plan what observations the robot can make or should make, excuse me. So those observations can be determined by the robot autonomously on its own when it's out of communication in order to continuously be operating by analyzing the map and determining what areas the greatest information can be gained by further sampling. This requires interpretation of the data in the map and a planning process that can make those selections. This is an experimental design problem where you're choosing what the next most informative sample will be, or next most informative sequence of samples. So once the robot has made observations on its own, it can transmit those back to human scientists, or it can use those observations to update the map directly if it's able to interpret that scientific data and from those interpretations, modify the map or update the map with new and better information. So what we see here is a virtuous cycle of a map that's being planned against, then further observations that improve the map that can occur directly on board our robot while it's operating continuously out in the world, and then periodically transmitting that information back to Earth, since the purpose of exploration is always to inform us and learn more about the world. So how do these parts work? I'll first mention how we build that map using the observations, interpreting them automatically. There are a number of different techniques actually, but one recent result focuses on building geologic maps automatically. So having a robot that can not just travel the ground and take pictures, but actually determine the mineralogy and begin to build a geologic map of a site. So it's built on the interpretation of instrument data, and we use spectrometers. So these are devices like a camera, but instead of taking a single RGB image, a spectrometer measures a large number of wavelengths at each pixel. So we have a continuous spectra you see there in the upper right, and that spectra tells us not just the appearance, but also can tell us things about the composition of the object that we're looking at. So we can look at absorptions in different wavelengths and determine things about the mineral content, sometimes the atomic content. You can detect things like chlorophyll and where water is absorbed in the spectra. So if we can interpret those measurements, starting with our initial estimate, we can then, as we take further measurements, reduce our uncertainty around the spectra. And in fact, we can begin to reconstruct the high resolution spectra from a sequence of observations in the area around the robot. What you see in that evolving graph there is actually a model of the entropy, so the uncertainty in different places in the world. And as the robot moves around, you see a white path there. It's taking measurements, and the overall entropy in the scene, which begins highly yellow and gets darker and darker as the entropy is reduced, comes down, decreases as the robot explores. And one thing to emphasize here, by taking just these few measurements at the points where the robot has observed, we can actually reduce the entropy over the entire area by reconstructing the spectral signature at every place using the local information and essentially extrapolating to greater and greater distance. Once we've reconstructed the spectra at each point in the map, we can then use classification techniques, again, a variety of strategies here, but essentially classify those spectra into, in this case, particular mineral types. So this adaptive exploration then, once we are reconstructing spectra and then classifying into mineral types, starts to look like what you see here on the right, where as the robot is traveling the terrain, it's collecting spectra, it's classifying the spectra into different minerals, it's deciding where to go next in order to best reduce the entropy or uncertainty in its model. And it's discovering new minerals as it goes. So we begin in one area and find some new minerals. And in this particular instance, there's a third mineral type that's very similar to what you see in green, that's not initially distinguishable from the prior, from the coarse orbital information. But as the robot collects spectra on the ground, it's able to make that distinction and then map out this third mineral type, not just in the place where the robot visits, but in the areas that it now can interpret as being spectrally similar to that new mineral type. This is built on a Gaussian process model that's updated with each of those measurements. And through that Gaussian process model, we can do that extrapolation to all the places that the robot hasn't visited directly. As I mentioned, what we're trying to do is maximize the information that we gain for the effort put out. And so we've been doing work developing different planning techniques. Here you see three different strategies. On the left is a purely random strategy that's uninformed. The robot doesn't interpret the spectra at all. In the larger sense, it just moves at random. So this gives us a baseline of what an uninformed observer would do. So someone who's not a geologist is just walking around and looking at rocks. In the middle, a purely greedy strategy where at each step, the robot looks in its local area and decides what's the next most valuable measurement to make, which one is the immediate greatest reduction in entropy. And on the right, a non-myopic strategy, so a strategy that looks several steps ahead and tries to optimize a sequence of observations in order to more rapidly reduce its uncertainty in the world. We've been working with some new planners that are showing some very interesting promise based on ergodic metrics, where we consider not just the discrete sample points, but in fact, a continuous smooth path through the world and how that reduces our uncertainty. Let's give you a few little insight here into how these systems perform. We usually begin with a large simulation study running thousands and thousands of possible traverses in an area. And here you see how that random strategy provides an upper bound, but being a little bit more informed by interpreting spectra on the ground with the greedy strategy improves, and being able to look ahead and reason out a whole sequence of operations does even better than that. So the simulation study across the top, I just want to emphasize in the upper right there, we do show that this strategy of introducing entropy strongly correlates with the error in the final map. So when we're all said and done, we look at the geologic classification that the robot has produced and compare that to a prior ground truth map that has been made by field geologists. And you see that very strong correlation, so that we know that when the robot acting on its own takes measurements in order to reduce uncertainty, those actions are going to lead to producing a more accurate model at the end. And we verify this in the charts in the bottom. In an actual field experiment, this is performed in a site in Nevada, where, again, the trends follow what you see in the simulation that's been run over many, many thousands of operations. We had the great good fortune of being able to repeat at 3 different sites a number of different times, running the same traverse that we had previously analyzed in simulation. And as I say, in general, the trends follow. We're getting new work here that's producing even more accurate results. I wanted to mention, in fact, in the introduction, it was mentioned the Moon Ranger project. So this is a project that we're we're executing at Carnegie Mellon to develop a very small planetary rover, so about 17 kilograms, roughly the size of a microwave oven, to go to the South Polar region. We're working on the landing site selection, but close to the South Pole, where we know there's abundance of hydrogen. What's interesting, I think, for this group about this type of robot, it represents, I think, a new class of explorer. It is smaller, but more intelligent than the previous explorers, in that it has to navigate autonomously, continuously. So it's always going to be moving. And it's going to record this information about hydrogen abundance and give us a first look at the distribution of water ice in this one cratered region. It'll be followed shortly afterwards by a few more rovers that are more of the class of Curiosity and Perseverance, that will have drills and many instruments on them. But I actually think in the future, we will see a shift towards the smaller, more intelligent, more independent explorers as we send more and more systems to the moon and beyond. So in summary, these robotic explorers are evolving from simple data gathering machines that execute commands to move from place to place and execute commands to take particular measurements into truly intelligent agents that perform science. And I want to emphasize that, again, this exploration is not just building a geometric map of the world, but building a scientific map of physical properties in the world. So where will we be by 2050 if we were to speculate? So right now, these robots, as I said, are able to decide where to go, what measurements to take, and develop a map that is more and more accurate. However, I think there are still challenges in generating hypotheses. So beyond just mapping the geology of a site, if you want to understand the evolution, or if you want to search for life, how do you generate hypotheses that the robot can then act on in the same way that it can act on these scientific measurements? And then once you generate a hypothesis, how do you plan the investigation, collect the evidence? So not just deciding where to go and what to measure, but really thinking in terms of evidence, where you maybe have a number of different instruments. They have different informative values relative to what you're trying to model. So how do you build up evidence for a particular hypothesis and really test the hypothesis or falsify the hypothesis? So when we imagine, for example, missions to Europa and vehicles that will travel under the ice and go tens of kilometers underwater to places maybe that harbor life of different types, in a scenario where you can't communicate with this robot for maybe days or months or even years, how does that robot execute that high level objective of finding life building on the kinds of things that I showed you here today in research, I really do think it'll take till 2050 till we start to answer some of those questions. So with that, I'll stop. Thank you very much.
Oh, thank you very much. Thank you very much, Professor Weathergreen. Okay. We are also joined once again by Moonshot Goals 3 Program Director and the project managers. So all panelists, please put your video on. So I'm honored to exchange ideas with such distinguished panelists and look forward to a lively discussion. I think this is a great opportunity, and I think some topics are very related to each other. So first of all, I'd like to ask three overseas panelists, Professors Goldberg, Mombauer, and Weathergreen, if you have any questions or comment about the research goals by the four Japanese Moonshot program managers, or if Japanese program managers have any question or comment about the guest panel's presentation, please say something. So anyone is fine.
Hi.
Yes, Professor Fukuda.
Yeah. Ken, how are you? Okay. So,
Very well, thank you.
I like your fog robot concept, and I like before you're leaving here quickly, I'd like to ask you because such a kind of fog robotics, such a kind of what we need, such a kind of scientific discipline, such, in terms of such a kind of co-evolution and self-organization in your fog robotics.
Well,
I think it's very helpful for such a moonshot program.
Yeah, well, because so many things we're talking about today are related to this broad usage of adoption of robots and the idea that they'll have to communicate both with humans and with each other. And I think that's a point, Toshi, that you've made extremely well here, is that the opportunity, especially because of our aging populations, we can all relate to that. Even I can relate to that now. And it is so important to be able to have robots that will essentially learn both how to get better over time, because I think every one of us is talking about that kind of improvement, and also to learn how to be tailored to the individual humans that the robot is interacting with. So humans are very different. We have different preferences, and we like things to be done a certain way in our homes, for example, or in our laboratories or workplaces, or even on Mars, right? We would want, or on the moon. So having robots essentially be in communication, of sharing information, is, I think, going to be very important and facilitated by the advances in networking. Of course, we also have to worry about the potential dangers of this. And some of the comments and the questions have come up and raised those questions as well. And I think the key is remembering that we see the robots as complementary. And Fukuda-san, as you said, that they're something that the robots will enhance us and our abilities to be effective in the future.
Can you tell me more about such a kind of life 2050, including such a kind of artistic kind of, or such a kind of how to enjoy life? You are an expert of the artistic robotics. I know we worked together several years ago.
Well, I think that in the artistic side, that we are. I hope, first of all, that I make it to 2050. That's optimistic, but I'm hopeful. But one of the things I think is that we will see art and as Katya mentioned, also that in terms of dance and movement, that we actually learn a lot about our own questions, our limitations, our challenges through art. And that's where I'm very excited, because I hope that the program, the Moonshots program, will also have room for creativity and exploration in that way, because that is going to open up the doors to new ways of thinking and also engage with students who are going to be the future.
Thank you very much. It's very nice to listen to you, and also kind of Kaja Momba-san, also David Weathergreen-san, such a kind of scientific kind of exploration to cope with such a kind of human soul thing. and everything covering such a moonshot problem. Thank you very much. Ken, you are leaving soon, yeah?
Well, I'll stay as long as I can because I'm really fascinated by this conversation. So,
Okay. Okay, thank you. So sorry about that. My network was down. Yeah, but I recovered. Any other question or comment about the panelist presentation?
Hi, can I have a question?
Yes, please.
So, yeah, about AI, there are many discussions about from the point of view software. So there are a few discussions about hardware design. So I want to ask for panelists from foreign countries to how do you think the hardware design will be the relation to the AI development? Ken, hello.
oh, it's for me. Okay, I can.
So first, you leave soon, so I will ask you first.
Okay, thank you, Sagano-san. I think that this there's going to be a lot of change in the design of arms. For example, as we see, there's a lot of progress toward more collaborative robots that can interact with humans because they're not as dangerous. Right, they're compliant, and that because they have to work in close proximity with humans, either in the factories or in homes, and that's already requires a certain element of intelligence because the system has to detect contact, right, or danger. So having cameras or other kinds of sensors around, and then being able to process that very fast so they can stop very quickly without injuring a human. That's going to be very important. I think that the design of the arms themselves in terms of new motors and new actuators is going to be very important. Harmonic drives have had a big impact. Being able to control those, to be able to compensate, for example, for lightweight and low cost motors, to be able to achieve high precision without having very high precision motors. That can be done if you can close the loop with vision. So again, where AI comes into play. And in one area is surgical robots, where there's again it's very challenging to work with the cable-driven robots. And Fukuda-san knows about this because he works with them. These robots are very imprecise, and I think many of you do. And so, how do we compensate? Again, we try to build control, and as actually Nagatani-san mentioned this idea of the open design, which I think is very interesting, and how we will incorporate that to have the dynamic collaborative control. Maybe you can say a little more about that in the context of AI.
Thank you. So how about Professor Momber?
I guess I would just
Please
quickly
turn
add
on the
that
microphone.
Sorry. Okay, so I think with respect to hardware, I think a very crucial point will be to build robots that are at the same time strong but safe. So right now, most of the robots that we are closely interacting with, they are kept safe by keeping them quite weak. So having robots that can produce high torques and do all the tasks we want them to do, but at the same time interact with humans in a very safe way. I also think that soft materials will play an important role, like for soft materials, especially for all these mobility assistance devices I was mentioning, but also soft surfaces for humanoids or companion robots working with the humans. So I would say that for things like exoskeletons, we will probably in the long term move to completely soft devices once the strength can be handled with soft materials. But probably with companion robots, at least a soft shell would be required. And then also soft actuators would also be a very important topics, and more bio-inspired actuators. I think that's very
Thank you.
important things.
So Professor Watakunin, please.
Yeah, I guess maybe to add, I see an increasing diversity in forms of robots as we go forward. One of the areas I work in is agriculture, right? Where the classic paradigm in agriculture is a big tractor. But what we're seeing is that as we're able to embody more intelligence in the robots, they can get smaller, they can take multiple forms so that you have collections of heterogeneous robots, each one different, specialized to capability and task, maybe specialized to environment, but through intelligence, able to work together to perform tasks. So things like harvesting specialty crops, you can have a group of robots working together to expose materials, collect the fruit, and transport it, where in the past we would have had one large industrial machine sort of crashing its way through the field and pulling those materials out. And I really think that it's intelligence and AI as much as improvements in hardware that allow these heterogeneous teams to work together. And we'll see that in many, many different areas as well, beyond agriculture.
Thank you very much. Yeah, Toshi, Fukuda sensei always said that co-evolution is very important between human and robot, and also the robot hardware and AI. So I will ask, and I want to discuss this about this.
Yeah,
Thank
okay.
you.
Yeah, thank you very much. So now we would like to discuss how to tackle co-evolution and self-organization that integrate AI technology and robot technology. So it's a bit vague topic, and but first of all, I'd like to ask all of you for your opinions on this topic. Okay. So who is first? Fukuda sensei?
No, I don't listen to all others.
Okay. Okay. So the first.
Can I say something?
Yes, please.
Yeah, this is KG.
Mm-hmm.
And thank you very much for the Professor Goldberg mentioned that about open design. Actually, at the beginning, before thinking about the AI, we think about we need bigger machines for working on the disaster response type robots. However, we think bigger and bigger, and finally, we found that it's a kind of infinity. Then we are reaching to the open design actually. So to tell the truth, I have no idea actually about the open design, but we have some ideas, but I cannot explain in detail. However, when David speaks about agricultural things, and also we are thinking about the same thing. So on the moon, actually we cannot carry a heavy machine, and we cannot dig with the same way on the moon. So I'm very curious about David said moon rangers, the weight of the moon ranger is 17 kilograms. It's a pretty right. And I wonder if how you cope with that. Then after that, I'm not sure, but my idea is that we need an open design for robots, and also that we need the almost the same type of the AI side. Actually, this time the current AI technology requires the many data for learning, but on the moon or in the disaster site, we don't have much data. In that case, how we cope with the situation. So I also think about open AI or something we need actually. This is I'm not sure what kind of AI, but in my mind there is some kind of concept should be required for the co-evolution between the robot and the AI. Okay, thank you very much.
Thank you. Okay, so Professor Harada, how about this topic?
Yes, thank you very much for asking. And so as for the co-evolution of human and robots, I really like the word complementary that Professor Ken Goldberg mentioned. So I think that, we tend to discuss which one is better, AI robots or humans, but we are just different. Robot has different sensors, different structures, and different dexterity. So I start to think that the AI robot should have their own way to understand the world, their own way to evolve themselves. So now we tend to let the robot do the human-like tasks, but probably what we can do is just to give opportunity or how can I say option that the human robot can investigate to seek in their own way. Then we start to discuss how we appreciate the difference between human and robots and how we want co-evolve with robot. That's my thought.
Okay, thank you.
I just want to follow up on what Harada-san said, because I think that is very interesting in the context of the kind of scientific discoveries systems that she's talking about, where I'm thinking of something like what we've seen in the last year over systems to try and analyze the COVID-19 virus. And it's very interesting because there's humans, but they're working very closely with machines that are sequencing the samples of the virus, trying to come up with vaccines, doing protocols and experiments. But imagine that could be facilitated again by a worldwide network of individuals and machines. And I think you're absolutely right, Harada-san, because it has to evolve, because what we knew a year ago is very different than what we know today.
Yeah, and we also need to pay attention to the difference between the lab automation and the robot for science discovery. There can be, they are also complementary, in my opinion. So I thank you very much for your comment.
Okay, thank you very much. So, Professor Hirata, how about on this topic?
Thank you very much for asking. So as I mentioned in my presentation, I believe that AI robots will be everywhere and will be shared and used. So in such a society, it will be necessary for AI robots to be selected according to the user condition and to provide assistance tailored to the users. So in our proposal, a large number of robots can be appropriately selected to provide assistance to a person. So we are also proposing a robotic nimbus where the shape and form of the robot can be transformed. So in other words, there are many parameters and options to control our proposed AI robots in order to provide appropriate assistance to a person in such a situation. So where there are many options, it is necessary for both AI and robotic technology to co-evolve in order to derive robot from that is suitable for human and to derive appropriate assistance method according to that form or shapes. So in addition, sharing the assistance of many other people will lead to the discovery of new assistance methods that have never been used before. So furthermore, by watching over a person for a long time period of time, that AI robot will be able to provide not only the best support at a certain moment, but also the appropriate support to the person from a long-term perspective. So I believe that this can only be achieved through appropriate co-evolution of AI robot technologies. So this is my comment.
Okay, thank you very much. Okay, so next speaker is Professor Sugano. Please say something on this topic.
Yes, so co-evolution. So
yeah,
I believe that the most important point, how to understand the human. So robot, how to understand the human dignity or human character, personality, that communication and interaction between robot and human is very, very important. So robot must be able to understand human dignity. That's a very important point. So then also the human should understand the condition of robot. So I I'm not sure, but that over 2050, so the robot will very similar to the human body and intelligent or emotions. So that very say in the mind. So the robot has mind and the human has mind. What is the relation between them? Of course, that we should consider about ethics. However, we should consider that robot as a tool or the friend or the some companion. So which is better relation between human and robot? So I don't have the answer yet. I don't have the answer yet, but we should. I now it is easy to discuss this situation. Rather, I I want to aim that goal is a robot can understand the human dignity and character and personality and sense of values. That is an important point between human robot relationship.
Okay,
Okay.
okay, thank you very much. So Professor Mumbauer, so please say some comment on this topic.
Yeah, on the co-evolution. So I think we have to distinguish between the cases where the robot takes the role of a person and replaces a person in some sense, and I think we really have to make sure that it's done in a generally socially accepted way, that robots are really taking the jobs that either there is no one for because there's really a shortage of persons, or the jobs that really nobody wants because they are too dangerous. So I think there definitely should not be such a competitive situation of people thinking that robots take their jobs away. And I think that's probably less a danger in Japan than in Western countries. I have the impression it's really it's still a really big fear that robots might take jobs away. And yeah, I think there's we have seen so many situations where there was a clear shortage and where robots could have helped a lot. So I think it's important that we start with these areas and that people see really the benefits of robots. Then I think in the case of the mobility assistance devices I was showing or was trying to show, unfortunately you didn't see them. So I think in that case there's not this competitive situation. So in that sense the robots are more replacing the bad previous devices. But I think here it's also really important that they are also really adapted to the individual person, so they meet the individual person's need, meaning they fit to their body and their requirements of support, but also to their personal preferences of how that support should be done. If they like really strong, really fast motions, if they are more careful persons or more energetic persons. So I think a lot of adjustment is required in order to be to really have accepted robotics technology, and we need a high adaptivity and also good AI technology in the background to allow for that adjustment to happen.
Yeah.
Thank you very much, Ken.
So I want to actually, Sugano-san made me think of something, which is the relationship we have with our robots. So there's been a study recently with robots of the kind of robot that we have at home today, which is the voice activated Alexa type of systems, which are, by the way, I would say very surprising effect where that didn't exist and then suddenly it was everywhere. I mean, is it as widely adopted in Japan as it is in other countries? Those systems, the sort of voice activated, system on your table that basically will tell you the weather or play music or answer questions. So the reason I bring it up is because there was a study that children who grow up with this become very comfortable giving commands to the system. They say, "Tell me a story, play this." you know, and then what happens is when they have the human babysitter comes, they start telling the babysitter what to do. And they're very rude to the babysitter because they're used to just yelling out commands. So the reason I think it's very interesting is that could that be a problem if we have robots doing caretaking of children or senior citizens, and we get very comfortable basically treating them like servants without really caring about their dignity, and then when we have real humans that we might have bad habits. So it's maybe something to think about, and it's very interesting. I hadn't thought about this before until Sugano-san, you brought it up.
Yes, thank you very much. Yes. And so, contrary to co-evolution, and can AI and robotics have a negative impact on each other? As science progresses, we need to be aware of light and shadow at all times. So we'd like to discuss this topic. Does anyone have any comment on this?
Well, I think maybe that's what Ken was alluding to there, the idea that if we start with robots that are fairly simplistic and command-based, and that becomes our norm, then as they gain more intelligence, they seem more like, you know, our fellow humans, and we carry our behavior over onto other humans. I was going to share just an anecdote about working with these robotic explorers. I've been working with planetary scientists, biologists, geologists for a few decades. And when we started, the robots were not as capable. And the scientists were initially skeptical that they could do anything useful at all. And then they were disappointed when the robots were sometimes successful and sometimes not successful. But over time, as we were able to show some of the capabilities where robots can excel, like to know exactly where they are and to repeat the same operation exactly the same way each time, the scientists became more confident. And I'm noting a comment or question in the chat here. Our scientists stopped referring to the robots as it and started referring to it by gender pronouns, usually she, if it was sort of alluding to the model of a ship referred to in the female. It was really interesting to see that not only did they act more familiar with the robot as their confidence grew, but they actually would start to treat the robot like a teammate and be enthusiastic or cheer for it when it's successful. So I think that's, maybe that's part of human nature, that as the robots become more like partners, we would hope that we treat them well, because that then reflects on our fellow humans. So I do think there is that danger that you mentioned, that we treat robots like machines, and that leads us to treat others like machines. But the opposite, I think, also could be true if we're careful and we involve the scientists, social scientists in particular. We could actually learn better behaviors by setting up our system so that they encourage us to treat robots well and then treat each other well.
Okay, thank you. Any other comment on this topic?
I have another comment. I have a question, if I may.
Yeah.
I'm curious about the role of industry in the Moonshot program, because I'm very aware of the great research that goes on in industry in Japan, and for example, Toyota has been major progress in research fronts, and in particular home robotics and autonomous cars. I'm curious to what degree industry is engaged with the process and with the program.
Yes, I'm encouraging such a industry to work together with this kind of Moonshot program. So, like some project manager working together with the industry, particularly Nagatani-san, he's working with the industry, such as civil engineering, all the things. So, but those kind of things should go to the industry. I mean, as that's a kind of aim or goal of this. Also, not only making such a research work, but also make such a kind of industry impact to the industry and to make such a kind of social benefit. That's important, as you said.
Yeah, I want to make a additional comment about that. Actually, I tried to invite some other big companies, but they don't want to do that because they don't want to fail, actually. However, the smaller company is much better to have a cooperation with us because they want to go up, actually. And finally, the best partner for me is in the local side, not in the Tokyo or Osaka, but for example, Kyushu Island or Tohoku area. These guys are very interested in, and also they have actual fear of the decreasing of the labor in such kind of the local place. That is the kind of my driving force for me. That's all.
Mm-hmm.
So I have one comment about the industry. So now I'm asking the several companies to cooperate with us. So fortunately or unfortunately, my research focus is nursing care. So the company of the nursing care is not a big company. So that there are so many small companies. So that I asked the several companies, and most of the company has a positive answer. So I think this is a very nice. And then, but unfortunately, small company cannot do the research or cannot cooperate with other companies. So that from the academic side, we can link all of the company together. So I think this is a very important to accelerate this kind of research.
Yes. Yes. Yeah.
If I may add a question to Hirata-san, are there nursing homes involved in your project? I mean, do you have a really deployment in real life situations, or will it mainly be in the lab?
My research target is nursing care, so that we'd like to implement my robot system in the nursing care homes or hospital, and we'd like to use our robots as a rehabilitation. So this is the first target. So of course, our research could be applied to many other fields, such as sports coaching or another child care and so on. But firstly, I focus on the nursing care.
Yeah, but the question was, do you have partners in the project who could directly implement it, like a nursing home or a hospital?
So you mean the partner is a company?
Or no, not a company, but a hospital or a nursing.
Yeah. So we have many partners. So now our research member has one of research member is an institute or a hospital of the care home or care hospital and so on. So that we have many partners for implementing the robot system.
Okay.
So in Moonshot Goal 3, there is also collaboration between the academia and the industry side. Yes, exactly. Okay, so any other questions from panelists for discussion?
Yes.
Yes.
Right. So since I thought Ken is leaving soon, but he's still here. Okay, that's great. Thank you very much, Ken. That's a kind. So since there's a kind of scientific discovery, David-san, also Kaja-san, you have a kind of social human interact HRI. So that's also David-san, you mentioned such a kind of space exploration, also like kind of agriculture robot too. That's a kind of so that's a kind of very interesting. Such a kind of distributed robotics, also like such a say like a heterogeneous such a kind of a module or robot work together, something like that. Based on my research work, so the last 35 years, such a kind of a reconfigurable robotics. That's a kind of field. We need such a kind of a good intelligence, such how they can distribute such a index. How do we make such a kind of a complex system from the simple robot module? So the interacting to those things or combining those something like that. So Davidson or Kaji-san, can you tell me more about such a kind of about those areas, such a kind of what you say, kind of self-organization and also kind of co-evolution in your field, particularly such as space or agri, the robot work and the social HRI. Thank you.
Before they answer, now, if I may, I just wanted to say I want to thank you all, and I think the answer to my mind of that question, Fukuda-san, is exactly what you're doing today and what you've done throughout your career, which is being very, very comfortable talking with people from many different backgrounds. And the fact that we're here today is a perfect example of the kind of interactions that you've been pioneering for Japan and for the IEEE and really for the world. So I want to thank you personally and for your whole career of doing this. And I apologize, my family is having dinner tonight. It's a special night for us, so I must leave. But I thank you so much all for your comments today. I learned a lot, and I'm very excited to see this project and see how it develops. Thank you.
Okay, thank you.
Thank you very much.
Okay. So,
Yeah, any other questions from panelists?
David-san, you mentioned such a kind of importance of such a heterogeneous robot, and robot work together. This robot work together instead of kind of big robot, small kind of robot. For example, you mentioned those things. Can you tell more of such a distributed intelligence or something kind of how they can develop more in such a kind of evolutionary robotics?
Yeah, so teams of heterogeneous robots, how does that evolve? Well, I do think that will be a challenge for the coming decades, because right now we typically engineer those individual robots to work together, but the type of work that you mentioned, where the robots themselves can change their form, I think holds great promise for the future if we can start with teams and they evolve and change so that they're better suited to their task, or so that they can adapt to changing tasks. This I think will be, it's an AI problem to understand how that development, how that evolution and change of form needs to occur. And it's also a hardware and robotics problem, trying to create these robots that are adaptable and changeable as they evolve and improve, but as the environment and the challenges change. Right now, we engineer things very specifically, but I think in the future, these systems becoming more adaptable and having the intelligence to know how to adapt, I think will be a great benefit.
Yeah, thank you very much. So you give us an important keyword, adaptive exploration. So like humans, yes. Thank you very much.
Yeah.
Any other, yeah?
If I may add, I mean, I personally find it very still hard to imagine how machines can permanently reconfigure themselves. But definitely, I mean, the way machines or robots look is very important for their acceptance and for like it's important for the physical interaction, but it's also very important for the social interaction. And there also were questions in the chat about how we work with other, like with social scientists or with other. I would like to emphasize that for our research, these international collaborations with non-technical people, with social scientists, but also psychologists, Then of course also for medical experts from all areas, also gerontologists, geriatric people, that's very important. But then also also get health insurance involved, get all the stakeholders involved that may contribute to the acceptance, and then also speak with the patients, but also the relatives, the carers, and like know all their requirements to in the end not have a technically great product or robot, but also one that meets all the other requirements. So I think that's very important. And should not be be forgotten in any project.
Yeah.
Thank you. It's great to hear that this is also integrated in the Moonshot project. So.
So physical and the social human robot interaction is very, very important here. And also you gave us a keyword, motion intelligence. This itself also co-evolution AI and robotic technology, I think. Yeah.
Yeah, for the robots, I mean, yeah, that's very important to have. The robotic technology, but also the AI behind, and also have the AI like take into account that robots are particular and that robots are embodied, and that there is this constant interaction with the real world. That's really something the AI has to be adjusted to. So.
Yeah, thank you very much. Are there any other question or comment from panelists? Okay, no, so it looks like our time is up. I think we received a very valuable comment from everyone and had a meaningful discussion. Thank you, everyone. I'd like to close this panel discussion by once again thanking our distinguished panelists. Thank you very much.
Thank you.
Thank you very much.
Thank you.
You're welcome. Thank you.
Thank you very much.
Good luck with all your great
projects. Bye.
Really interesting.
Thank you very much for all PM. Thank you very much.
Okay, thank you, Professor Ueda. That concludes session 2. When you leave Zoom, you'll be redirected to our questionnaire. We look forward to receiving your comments. Please note it is the same questionnaire for all sessions, so you only need to answer it once. The final session for our International Symposium, session 3, will start in around 10 hours. For our audience in Japan, we also have a local kickoff symposium today from 1 p.m. to 5 p.m. We look forward to seeing you there. Goodbye.